So I want to talk about how you really require multiple techniques to fully characterize inhabited worlds, not to mention potentially habitable worlds or any worlds. You know, we're sort of used to it, but I think the whole question of finding inhabited planets, at least with primitive life, I'll try to emphasize how you need all these different techniques. First thing I want to highlight is this great quote by Auguste Comte, who in the middle of the 19th century said, "We'll never be able to study the stars by any means to understand their chemical composition." Well, turns out we could do it with stars, and we're already doing it with planets, and we're going to be able to eventually get and find evidence for life. So a lot of what I'm saying here was in a paper that myself, Malcolm, Wes Traub and Carl Stoppelfeld, Andreas Querenbach, and Sarah Siga put together at PP5. I just want to emphasize the contributions of Wes Traub, who's fell very ill many years ago and was a real contributor, particularly to the coronagraphy, but also to interferometry. There are a number of people here who worked on the IOTA interferometer back in the day, and Wes certainly made a lot of contributions to this. But these are all people who looked at the different techniques we had available for doing exoplanets and really came to the conclusion that you need them all. So what makes a planet habitable? Well, there's simply the distance from the star. We see here the interesting bit, which is sort of the habitable zone, which is that sort of blue line depending on the luminosity of the star. You need a low eccentricity orbit for stable temperatures. Obviously, the distance to the star gives you the basic temperature. You want the long-term orbital stability in terms of other planets in the system. You want a low bombardment rate. You don't want to be continually hammered with comets and rocks from an asteroid belt or a Kuiper belt. And you want to have a low sort of UV and X-ray flux, at least during the time that you're trying to sit there stably and create or maintain life. Planet size and mass is really critical. You don't want to be too big or too small, no runaway accretion, but be able to retain an atmosphere. There's some arguments that you would like to have plate tectonics to have an active carbon cycle. That means your planet has to be sort of big enough to have plate tectonics and a molten core. You also want that molten core for magnetic field, for solar wind protection. In terms of composition, you need a decent surface temperature, so you could have liquid water somewhere. You need obviously to have some supply of water and the appropriate volatiles. And again, some arguments are that you'd like to have at least some solid surface for life so you can get higher concentrations of some of the key molecules. So what are the techniques that we use? Well, certainly dynamical measurements are really critical. You want to get the mass of a planet, and then you'd like to be able to combine that mass with a radius and figure out a bulk composition. You can see up here just, for relatively small size systems, a few to 3 Earth masses versus radius, what is the composition in terms of mantle, iron, Earth-like, and so on. You'd really like to have that information. You'd like the full orbital information, including eccentricity. You'd like to know about inner and outer planets and whether those planets are actually coplanar or not. From direct imaging, you can certainly get orbital positions at specific instants of time. That doesn't necessarily give you full orbital information, but it can certainly break degeneracies in orbital some of the parameters that could be uncertain from, say, radial velocity, like inclination. Obviously, you'll get composition from low-resolution spectroscopy. For what we're talking about, the space missions, maybe higher-resolution spectroscopy from some of the ground-based cases. You get brightness as a function of wavelength and time, and you get exozodiacal brightness. So 2 early results on Earth as a pale blue dot. This is from the original Sagan result, looking back at the pale blue dot, and you can see the oxygen band and some water. In the mid-infrared, you can see for Venus, Earth, and Mars, CO2 in the Earth, but also ozone very importantly, and water, and Mars just CO2. And you just see that the Earth is just a very, very rich spectrum, and that, I'll come back to this, that ozone is a very prominent absorption feature. And we'll see that ozone is a very good biomarker where oxygen could be quite challenging at low concentrations. So I want to spend a bit of time on this plot, on this graph. It is really the gist of my talk. So we have radial velocity or astrometry as the two dynamical techniques, and these are the four visible or remote sensing techniques that some sort of direct imaging, either coronagraphic, starshade, or nulling interferometry. These are sort of the techniques looking at scattered light of some sort, and then here's thermal radiation. So for really measuring your orbit, what is the orbit? Is it stable? And getting to a temperature, the radial velocities give you really an idea of what the temperature might be in a very broad sense, and they really give you the best information about the orbit itself. From imaging, you can get some estimates of the orbit, but not really anything definitive. Presence of outer planets, you may image some of them, but combination of RV and astrometry will make sure you have a complete census. Planet mass is really only possible with the dynamical measurements. And indeed, RV is still somewhat ambiguous because all you're getting is an M sin I. If you add in an image, you might be able to break that degeneracy. Astrometry gives you the full orbital solution, including inclination. Planet temperature, you can maybe make some estimates knowing where the object is located and making a guess at the albedo. But if you really want to make a measurement of the planet's temperature, you measure its spectrum from 7 to 15 microns or something like that. That gives you an effective temperature. You also have a flux. That simply gives you a temperature, and then from the combination of the flux and the temperature, you get a radius. You can again make possibly, you get that for albedo, or let's see, the radius here, you need to have some idea of the albedo, so you combine that and get a correction to the radius you measure here. And that's why I call these are joint observations, where you have a combination with other techniques to really give you the best answer. Again, the albedo, you want to have all the different wavelengths going together to understand what the reflectivity of the planet is. Surface gravity, you really need the combination of the mass, which you get from the dynamical measurement, with the radius that you've gotten from this combination of observations here. You can get surface gravity. You can also get the bulk composition. Remember that what Bertrand said, you don't really get the radius to within a factor of 2. That's the density, to a factor of 8. And, so this is really problematical here unless you really have good measurements of the mass and the radius. Atmospheric composition really comes only from the different direct imaging or interferometric techniques. The atmospheric composition, all these different things contribute there. Surface composition, maybe you can see something like the red edge in the visible. Clouds and hazes, particularly in the UV, somewhat in the optical. Presence of water is really the near-infrared and the mid-infrared. Biomarkers, really across this range, but you'd like to have some combination of biomarkers to really give you a very robust estimate of what's really there, both combinations of species that shouldn't be there in equilibrium, but also just a broad range of species to help confirm what's really, in Carl Sagan's words, an extraordinary claim demanding extraordinary evidence. I'll make the editorial comment that I think measuring ozone in the UV is never going to happen. It is just too hard. Whereas it is a slam dunk, easy experiment in the mid-infrared at low resolution and modest signal to noise. And you're certainly interested in the exozodi environment. Where do the volatiles come from? You'd like to have some amount of Kuiper belt to be able to contribute, or asteroid belt, but you certainly want to have a very clean system, both from the standpoint of just being able to make the measurement with low contamination from photons from the exozodi, but you don't want to just have a planet where you have to duck your head all the time for incoming debris coming in and landing on your head. So I'll just say that the search for life requires many techniques and many decades. Cosmology started off, as many of you I hope will see on your tour of Mount Wilson, with this telescope almost 100 years ago, where it discovered the galaxies, went through Hubble, and now James Webb may finally put cosmology to bed. We can give up talking about cosmology after we get all the Z of 15 galaxies, and maybe Charles Lawrence gets one more CMB mission. So that leaves the next big question, finding life. So exoplanets for finding and characterization will be broad and rich, as was cosmology all during this time on many time scales, and that's important for keeping people engaged in the field. There's going to be lots of exciting midterm efforts to characterize everything from gas giants to super-Earths with Webb. And I've argued at every meeting that I've had on Webb for many years, it's one of 4 goals for the James Webb Space Telescope is to study exoplanets. So go forth and write proposals to use Webb to study exoplanets. It's real, it's now, it gives money, it gives great data, and we want to make sure we get 25% of the time on Webb, and so far we have been. And eventually we will get down to Earths. I mean, Webb may be able to do something on 1 or 2 of the TRAPPIST planets. There's certainly some intensive observations. The detectors have to work super well for the transiting systems to get down to the low ppms. Because remember, transit work does what your physics teacher told you never to do. Subtract 2 big numbers to get a measurement, to get a little number. If we get rid of the photons with coronagraphy or nulling interferometry, I believe we will get down to here, and that's going to be super important. Thank you.